Okay, so we are now officially recording. I'm only recording the actual presentation. So if you ask a question, then because the question will not, this will not be on tomorrow's test. No, because this is Unit 5 and tomorrow's test on Unit 4. Okay. And so anyway, I was about to say that if you ask a question, you'll hear me repeat the question so that the question can be heard. You won't be able to hear yourself on the video, which is something I asked us not to do. So if you ask a question, I'll probably repeat the question so the question ends up on the recording. All right? Okay, so here we go. Root of trigonometric functions. By the end of the class, you're going to be able to take the root of trig functions. So let's have a look here at a sine function. Typical sine function starts at 0, goes up to 1 at pi over 2, comes back down to pi, goes down to -1, then goes to 2 pi. You've seen the trig function for sine before, the graph before. So we don't get to say hi to your future students. No, you do not. You do not. So anyway, what if I asked you to approximate the slope of the, and remember, we're trying to figure out what the derivative of the sine function, okay? And if I asked you to sort of approximate what the slope was at 0, a lot of you would say it's probably 1, because this looks like it's, a positive slope and going this way. And I'm going to agree with you. The slope of the sine function at 0 is actually 1. So I'm going to plot that point, see if I can come up with a graph that represents what this derivative is going to look like. When I'm at pi over 2, when the function reaches up to 1, the slope of the function here is clearly going to be 0. So I'm thinking that the derivative function would be 0 at that point. When I get to pi, then it looks like the slope is going to be -1. It's now trending downward like that. And yes, the slope is -1. So I'm going to put a point down here to represent what the graph is going to look like. When I get to 3 pi over 2, it gets to this low point here again. So there must be a horizontal tangent here, which means that it's a 0 on this other function. And when I get to 2 pi, it looks like it gets back to the same slope of 1 we had before. So as I'm looking at this, right, and sort of tracing out the points that, let me just fold this over here a second. As I'm looking at, as I'm looking at this and sort of tracing out the points, I'm getting this line. And Alex is saying, this looks like it might be, so pi would be POI, right? Pi, yeah, actually, in terms of point of inflection, yeah, well, for this graph, the point of inflection would be at about 0 here and about pi. You're right. That's where it does change. Yeah, but I'm looking more at the graph now of this derivative here, right? It was a slope of 1 here, a slope of 0 here, etc., etc. And some of you are already looking at that and thinking, isn't that the cosine graph? So you're right. You're absolutely right. That does mean this, that the derivative of the sine graph is in fact the cosine graph. Absolutely. Right? Is a tan the second? Okay, we'll get to that. You're jumping ahead here. You're jumping ahead here. All right? Okay, so let's move on. Let's look at the cosine graph now. This is the cosine graph. Now, at the beginning of the cosine graph, yeah, you can tell that this looks like the local max here. So that means that it reaches the horizontal tangent here. So that means that it's a 0 slope. At pi, it looks like a -1. At pi, you're back to a horizontal tangent. So I'm going to put that as there. And when it comes to 3 pi, it gets up to 1. So I'm thinking, okay, this looks like this would look something maybe like that. So what are you thinking now? Do you think that you can come up with the derivative of the cosine function? Okay, Alex is thinking the secant graph. Is that what everybody is thinking? Renee says the minus sine graph. And Daria is agreeing. I think Daria is agreeing with Renee. I don't think he's agreeing with Alex. I'm not sure. Who are you agreeing with, Daria? Yeah, that's what. Okay, so yeah. So yes, the fact is that the derivative of the cosine graph is actually the minus sine graph. It's like you take your sine graph and you flip it upside down. That's what that looks like, right? So let me go back again. The derivative of the sine graph is the cosine graph, straight cosine graph, right? You would agree with Renee. Okay. The derivative, though, of the cosine graph is the minus sine graph. All right. Okay. That's good. That's good. Now let's get to the derivative of the tan graph. right? I'm not going to draw a graph this time. I'm going to remind you what the tan function is, right? Do you remember what the tan function is, folks? What essentially is the tan function? It's a ratio of two other trigonometric uh, ratios. It's this. It's a sine graph over the cosine graph. Thank you very much, Asia, Daria, and Renee. So, since that is the case, can we suggest a way that we could find its derivative if that is the case? I agree with you. Quotient law. Well done. So, we'll do exactly that. And here's where your skills with those trig identities that you learned back in grade 11 and use them again in grade 12 advanced functions are going to come in really, really handy. You'll see what I mean in a second. So sine over cosine means that if I'm taking the derivative of that, again, this is why this is much quicker. If I do this, it's going to be the derivative of the top, which is cosine. The derivative of sine is cosine. We just learned that. Multiplied by the underived bottom. So that's cos again. So it's cos times cos minus the derivative of the bottom is minus sine x times the underived top, which is sine x. Now I'm minusing a minus, which means it's a plus. Now, what does cos x times cos x come to again? When we multiply two cos x's, we refer to that as being cos squared x, correct? So what I have is really cos squared x, and because I'm minusing a minus, it's really plus sine squared x. So I have cos squared x plus sine squared x over cos squared x, and we all know that cos squared x plus sine squared x is 1. So it's 1 over cos squared x, which means it's secant squared x. Again, all of what we just did would have been the kind of thing that you would expect from a trig identity kind of question. So all of this works out to be the secant squared of x. When we get to some of these questions in a little while that we have to do derivatives of, some of those skills of simplifying trig identities are going to come in really, really handy. Now, I'm going to leave that to you, for those of you who are adventurous, to figure out what the derivative of cotangent of x is. Because it's actually very similar to this, but the answer is not just, well, I'll let you figure that out, right? But it can be done. It's easy enough for you if you follow the quotient law. If you put cosine over sine, which is what cotangent is, I'm going to leave that to you to figure out on your own. We don't have time to do that today, unfortunately. All right, so let's find some derivatives. Let's find some derivatives. And now this is going to allow us to use some of this stuff that we learned before, product law, quotient law, chain law, all that stuff that we learned before comes into play right here. Again, I've already written this all out, so it's just a matter of me clicking through it and you hopefully following along as we do this. So what's the derivative of 4 sine 5x squared? Well, remember that the 4 in the front can be just put aside for now. Just focus, because that's like a coefficient. You can multiply the result by 4 at the end. So really only focus on the sine of the 5x squared. Well, this is a chain law question, if you think about it. This is going to become, I leave that 4 on the outside like I just said. It's going to become the cosine of the 5x squared, right? That's the chain law at work because the derivative of sine is cosine. So it's a cosine of this multiplied by the derivative of the inside, which is the 10x. Okay? So, of course, 5x squared would be 10x. So this is what we have at the end of this. It's going to be the 4 times the 10x, which is 40x, times the cosine of 5x squared. There's nothing else we can do with this. We can't simplify this in any way. So when you get to that point, you can say that you have derived this function. So it's a nice simple one for us to start off with. Keep the 4 on the outside anytime you have, and it's going to have the same thing over here as well. When you have a coefficient, just a straight constant coefficient, put it on the outside, derive everything else, and then multiply by 4 at the end. That's my recommendation to you. So here is my derivative, and we can move on to the next one. Okay, so similar thing here, but now we're going to be using what for this one, right? You tell me, what would be a good strategy for us to derive 4x cos x? Product law, there is right. So we're going to do exactly that. We'll leave that 4 over here. Actually, okay, I didn't leave the 4 on the outside, but we could have. And I'm going to take the derivative of the 4x, which is just simply 4, multiplied by the underived second part, which is the cosine of x. Then I'm going to leave that 4x as it is. I'm going to multiply that by the derivative of cosine x, which is minus sine x. And yes, we can factor, and it's always a good idea for us to factor if we can. And there's no other thing that we can factor out of this except the 4. And like I said, if we had left the 4 on the outside and just derived x cosine x, we would have gotten this part on the inside here, and the 4 would be just left on the outside. So there you go. Right? Pretty straightforward, I'm hoping. I don't think any of this should be a struggle. If it is, please stop me. Let me know if there's any part of this that you want me to go over again. This is all on the whiteboard, by the way. So if you wanted to, and one option you have, yes, dear, go ahead. Okay, so you're asking, how did I get the minus x times the sine x? So remember, I'm multiplying these two things here, right? Right? So I'm factoring out the 4, and this would become a minus, and I still have the x there. So okay, let me show you what I mean then. Right? I can factor out 4. Hopefully, you agree with that. Then I'm going to have cosine of x, and then I'm going to have minus. Again, that's exactly wrong. Let me erase that. I'm just going to scratch it out. It would be minus because you have to multiplying a plus times a minus. The x is still there, and then the sine of x. All right, close my bracket. That's exactly what I have here, isn't it? Yeah. Okay, you're welcome. No problem. Again, I'm repeating the question. Can I go over this again? Just been a while, whole sine, cosine stuff. Okay, all right. So Mohammed is asking me to go over it again. So let me do that. Right? This is the product law at work. So part of this, Mohammed, is remembering the product law. Daria put product law and asked a question before. Remember, product law is when you say it's the derivative of the first function. Separate this into two functions. So the two functions are like 4x and cosine of x. Okay, Mohammed? And you derive this first and multiply it by the underived second part. That's where this first part came from. The derivative of 4x is just 4. The derivative of the cosine, where am I at? Hold on. Okay, so, and then the underived second part is the cosine of x. Okay, and then I'm going to do the same thing in reverse. I'm going to derive the cosine of x, which is the minus sine x, and multiply it by the underived 4x. Does that help you out, Mohammed? Okay, good. All right, so there's our answer, and I'm going to move on now. Okay, now you need to think about this as something that we just mentioned a while ago. This sine squared 8x really is this. It's the sine of 8x squared, right? I mean, we don't write it like this generally, but I wanted to make sure that you were clear that that is exactly what it is. It's when you take the sine of 8x and you multiply it by the sine of 8x, right? So once we write it like this, hopefully the next line is going to make more sense. Again, we don't normally write it this way, right? What you see me pointing to here is not the conventional way of writing the sine of 8x all squared. We normally say sine squared 8x. That's what we normally say. But this is what it means. So I'm going to use my good old, if you think about it, it's going to be the chain law here, right? So I'm going to take 2 times the sine of 8x. Then I'm going to multiply that by the derivative of the inside function, which would be the cosine of the 8x. Then I'm going to multiply that by the derivative of the inside of that, which is 8. And that's why I have this 8 on the outside here. Would I expect you to simplify this some more? Yes. So what does this look like? Just multiply the 8 times the 2. So 16, sine of 8x times cosine of 8x. There's a little more simplification that you could do with this if you use some of those trig identities, but I'm just going to, in the interest of time, just going to leave things as they are. So is everybody clear on that answer? I know some of you are a little bit rusty with all of those derivative laws that we learned like, 3 weeks ago? I don't know how long ago that was, but that would be the answer in that case. Yes. The 8 from. Okay, the last 8. Yeah. Remember, let me do this over here. If I ask you to derive, let's see if we can do it this way. Now, if I said to derive all right, we'll just use what's here. The sine of 8x, right? If I ask you to derive that, the first thing you're going to do is you're going to take the derivative of the outside function, which is the cosine of the 8x. Make sense? Okay. Okay, and then I'm going to multiply that by the derivative of the inside of that. The inside function is 8x. That's why I'm going to multiply that by 8. Do you remember that? No, it's not product law. No, this is not product law. This is a function of a function. The 8x is a function inside of the sine function. So it's a function of a function is what we're calling this. You're not multiplying. No, the 8x is one function which is buried inside of the sine function. So it's not like you're not multiplying sine times 8x, which is kind of what I think you're thinking. It's the sine of 8x. So that's why that is the case. Yeah, okay, good. Let me see if I can erase all of that from the slide. Okay, so that answer is done. If you wanted to go further, can you factor out the 8? Okay, no. No, you couldn't. But there is some scope. And so Sarujan's question is, if I wanted to factor out, can I go further factor out the 8? No. But there is a possibility here, right? I'll just say this. One of the derivatives that you'd have learned is the sine of, and this is, I'm not going to do this here, but I'm going to say this. The sine of 2x is equal to 2 sine x cos x sine x cos x, where they're both the same. There's a possibility that we could rewrite that using a sine of 2x on that one. But I'm just going to leave that alone for now. I'll accept that answer if that's the answer that you give me. But no, you cannot factor the 8 out of this bracket. No, absolutely not, Sharujan. That would not be right. Okay, let me just make sure we're clear on that. Okay. Let's come over here now to number 4. Sharujan, are we good with that? You can't just factor out the 8. Let me just say that. Does that make sense? Okay, good. Let me go over to number 4 now. Okay, so so what's happening here, right? What are we going to be using here? We've kind of used it before, but let me just throw it out to the class again and ask, which of the derivative principles are we about to use for deriving this function? Come on, folks, you know this. Product law again. There you go. Thank you, Renee. Thank you, Alex. Thank you, Baroka. Thank you, Daria. Product law again. Again, I think it's not a bad idea to leave the 4 on the outside for now, right? That's always, I think, a good idea. But let's keep going. So we have a sign up, and that's also going to be an application not only of the product law, but something that was it Zio just I think it was Zio just asked me. And this is also an application of the chain law, right? Function of a function. So let's get this done. So keep the 4 on the outside, which I think is what I'm doing here. I'm going to find the cosine of the 5x and multiply that by the 5, right? Because that's the inside function derived, multiplied by the underived second function, the cosine of 3x. That's what this is, the cosine of the 3x. Plus, let me now derive the cosine of the 3x, which gives me minus the sine of the 3x, times the 3, that's your chain rule at work there, times the underived first part, which is the sine of 5x. Again, see the 4? I leave the 4 on the outside there, right? And all I need to do now is just tidy things up a little bit. And what I'm going to do is take that 4 and let's see, that 5 and give me, I'm distributing that into the bracket. So 4 times 5 is 20. So 20 cosine 5x cosine 3x minus 12, because there's a 4 here, times this 3. So minus 12 sine 3x sine 5x. Okay? So yes, I do expect you to carry this through as much as possible. There's nothing else we could, this is already factored. So for me to put it in this form means I've actually taken it out of its factored form. And you might question whether it would be useful for us just to leave it in its factored form. Many times it is. Can you go over how you derived it again? Sure, Irfan. So Irfan is asking me to go over it again. So you need to remember how product law works. The product of two functions, right, Irfan? Two functions. Leave the 4 out, right? You see me to put the 4 on the outside here. Derive the sine of 5x. That's what this is. The cosine of 5x multiplied by the inside function, which is 5. So that's the derivative of the 5x there, Irfan, times the underived second one, which is the cosine of 3x. Okay? Still confused why the chain rule comes into play? I think what you need to do is do some revision of the chain law. Go back to that video. And again, that's what that block 4 period would be a good way for us to go over some of those questions of the chain law. When you have a function of a function, you're taking in this case, let me just underline it here. You're taking the function sine of another function, which is the 5x function. That's what that is, right? It's two functions that are sort of mushed together in a sense. So instead of saying the sine of x, it's taking the sine of 5x. So that is a function itself, right? And by the way, if this had been the sine of, let's just say, 3x cubed, just as an example here, then that would have been the cosine of the 3x cubed times the what is that? 9x squared, right? You see what I'm saying there, Irfan? Right, that's your chain law at work right there. All right, okay, hopefully that helped you out. All right, so let me put back the answers. Let me first of all erase all of this stuff here and put those answers back, or put that answer back that we had before. And let's move on to what, yeah, I'm not even sure why I'm factoring that 4 out again. This almost seems like I'm going back to what we had up here before. So anyway, let's move on. Yeah, factoring it is always a good idea. It's always a good idea to have it in factored form. And then you can see, let's see if you find a 0 or something like that, then that can usually help you out. Okay, find the derivative of the function, of the following function. So now we're bringing in the tan function, right? Again, same notion of leaving that minus 6 out, but now we have to remember what the derivative of tan is. And of course, put the minus 6 on the outside. I think it's a good idea. Wait, so we should factor it again. Alex, I really, let me go back to that a second here. The truth is, I probably should not have put this middle step in, because multiplying it out wasn't a good idea, to be honest with you. I would have said, I would think that this, let me do this. I would say this is not a good, that's not a good strategy, right? Because what I have done here is just simply brought the minus 3 sine 3x plus 5x back down here. So this is a better answer than this answer here. I wouldn't have put that answer in. So I agree with you. I don't think putting that 20 there was a good idea at all. Just factor it. Okay, Alex. In fact, it was factored before, all I did is I just recognized that the plus minus is really just a minus, is all I'm saying. Okay, all right. So Alex makes a good point. Let me say that. Okay, so, and make sure that she's pointing out that I was probably not as efficient as I could have been. All right, next question. Derivatives of tan functions. Now, well, we learned that tan has its own derivative, so let's go. Here's the first step. Leave that minus 6 out. I always say that. Then take the secant squared of the 5x squared plus 4x, which is what I've done here. And this is what I'm saying now, Zia. Multiply that result by the derivative of the inside function, which is the 10x plus 4. The derivative of the 5x squared plus 4x is 10x plus 4. So all of this is a derivative. Okay? And what have I done here? Did I multiply this out? Yes, I just multiplied, because these are all three things being multiplied. I factored out the common factor out of this, which is 2, right? The common factor of 10x plus 4 is 2. Then I multiplied that 2 by the minus 6, which gives me this. Okay? So this is probably the best way to write. It's just a multiplication of three things. It's not really, there's no factors here or anything like that. It's just three things being multiplied, a product of three different things. Okay? All right, moving right along. I think we're making some pretty good time here. Using the PowerPoint is probably not a bad idea. And then, of course, you're going to have the video as well, so you can always slow it down as you're going through the video later on. Let's get to number 2 for tan functions. Y equals 4 over tan 5x. What do you think? Is there? I am making the video right now, Irfan. I said earlier on that I was going to record this session. So all of what we're doing now is being recorded, minus your interaction with the class. So that's not going to be part of this, but it will be there. All of what I'm saying will be on the video, unless I clicked on the wrong box somewhere. And I think I did that one time at my other class where I forgot to put the audio in. So it was just video and no audio. Very, very frustrating. But anyway, back to this. What would be a good way for us to derive this? 4 over tan of 5x. Raise the exponent, Asia says. So you're saying do this. Look at you. That's it. I would not have used the quotient law on a question like this. I absolutely agree with Asia on this one. So put this tan 5x to the minus 1, right? Raise it to a negative exponent. That's what I would do in this case. So then I'm going to go ahead and use that same chain law again, right? So what would the chain law say? Multiply the minus 1 times the 4. There we go. So it's going to be the tan of of the 5x to the minus 2. We haven't done anything with the tan yet. All we're doing is using that power law of logs. So the minus 4 tan of 5x to the minus 2, that's the first part of this. And then we now find the derivative of the inside of that, which is the secant squared of the 5x. And then the chain law now comes into effect. There's a couple of steps here. The chain law would now say, bring that take the derivative of the 5x and make it just simply times 5. No, we can do more with this, folks, right? And a case like this, I would expect more from you. So we have tan and we have secant. What am I expecting from you? Let me show you what I'm expecting from you. This is what it's going to look like before we do anything more with it. I'm taking the 4 times the 5, which is minus 20. I'm taking the secant squared of 5x, putting it on top. Taking this tan of 5x to the minus 2 is essentially tan squared of 5x if I put it at the bottom, right? Remember, this is to the minus 2. So if I put it on the bottom, it means that I'm raising the tan of 5x to the power of 2. Now, this can be tidied up. And my expectation is that you would. Now, I tell you I was going to give you a test on this. I think I'd have to give you at least a little bit of a quiz, like a 20-minute quiz, something like what we did. I mean, like worth maybe 5%. So I don't think and there's no exam. So I mean, there's only one opportunity for me to have some assessment of this. So yes, I probably will give you a quiz, and I'll tell you more about that on Monday as to when that would happen. At any rate, this can be tidied up. Okay, I think I just dropped a bomb on you now. So people are fan, go for it. Okay, so what am I expecting of you in a case like this? Well, I have secant squared over tan squared. Now let's take away all the 5x and everything else, and let's just talk about secant and tan for a minute. Secant, remember, is 1 over cos, right? And I'm putting that over tan. So the secant is 1 over cos. Bear in mind that's what it is. Tan is sine over cos. So if I take 1 over cos and divide it by sine over cos, then effectively I'm multiplying 1 over cos by the reciprocal of sine over cos, which is cos over sine. And yes, that works out to be 1 over sine of x. Okay? And 1 over sine of x, of course, is the same thing as cosecant x. What does that mean for this question? That you could literally simplify this as the following: minus 20 cosecant squared of 5x. Okay, so am I expecting this of you? Yeah, kind of, yes. Okay, I really, in a grade 12 calculus class, with all of that math under your belt, 4 years of intense high school math, I do expect you to be able to take this and make it into this. Okay, all right, let's move this along. 4x tan 4x cubed tan 5x. I think everybody should be able to do this, but let's just do it anyway. This is the last one before we get to actually working on some tangents. So what's the derivative? Take the derivative of the first part, which is a 12x squared, times the underived second part, the tan of 5x, plus the underived first part, 4x cubed, times the secant squared of the 5x multiplied by 5. Okay, there is a common factor between these two, and yes, I would expect you to factor that out. And that common factor is 4x squared, and that leaves you with what's left inside of the bracket. All right. Would I expect more from you? I think you can probably leave it at that for this one. Okay. All right. Find the equation of the tangent at a point with the given x coordinate for each of the following functions. How do I do that? When x is equal to pi over 6. How would I find the equation of time? Think back to when we did this before. Find the derivative first, okay? All right, Zia is definitely on the right track. So we'll do that. Whenever we're talking about getting tangent equations, we need to find the slope of the function at that point and then build our equation line from that. So we'll do that. So what would be the derivative here? Well, I don't have to write anything. It's already in here. It's minus 6. The cosine of, remember, the derivative of sine is cosine, minus 6, the cosine of 2x multiplied by 2. All right, hopefully everybody is fine with that. And Darius is saying plug in the pi over 6 into the first derivative. But let me simplify this a little bit first. And putting, well, I guess I didn't really simplify it. Let's put the pi over 6 into it. So let's put the pi over 6 into this, as Dario just said, and absolutely right, in the first derivative. So the f prime, right, that's your first derivative, of pi over 6 is minus 6 the cosine of this. Now, here's where your work with special angles comes in really, really handy. So you can use your calculators. I'm not going to tell you not to use your calculators, but essentially this works out to be the cosine of pi over 3, right? Because you're taking 2 pi over 6, which works out to be pi over 3. So what is the cosine of pi over 3? And of course, after we get that answer, we'll multiply by minus 6 and multiply that by 2. Folks, before I click that mouse, what do you say that works out to be when you put all of that together? So minus 6 times the cosine of pi over 3 times 2. Come on, you all have your calculators there. Make sure, by the way, make sure your calculator is in radians. That's kind of important that your calculator is in the right mode. All right. So what are we getting here? Darius says minus 6. Baroka says minus 6. Are we all on the same page for that? I would agree, minus 6. Right? But that was only 2 answers though. So it looks like I need to do a quick room check here. Right? I want to make sure that we're all kind of following along here. So Fahad and Henry and Mohammed. Let me hear from all three of you. Fahad, Mohammed, and Henry. Okay. All right. Good, good, good. All right. So everybody's following along. I'd love for you guys to participate the way you saw Baroka and Daria doing a few minutes ago. All right. So, okay. So that's the first part of this. What is this telling us? This is not the answer. This is just simply the f prime of minus 6, right? What do we do with that? Because the question asks us for the equation of the tangent line. That's the slope. Absolutely, Asia. That is the slope of the function, right? The slope of the function, meaning the tangent line. So what else do I need to do at this point? Right? So now I know the slope of the tangent line is minus 6. That's great. But what do I do with that? Right, Sharujan and Asia, thank you very much for chiming in. I appreciate that. Right, we have the slope. Now, what do we do with that? Anybody remember how to get these tangent lines? Come on, folks, you can do this. We've done this. You've been doing this since grade 9. Right, finding the equation of a line. Find the b. Good, good, absolutely, Lily. But how? Lily says find the b. So we know the equation is going to look something like this. Y equals minus 6x, and then we have to find the b. But how do we do that? You can plug in the x into the original function to find the y. Thank you, Sharujan. So we'll do exactly that. Right? Let me erase all this junk here first. Right? The coordinate at the point of tangency. So we're going to plug, as Daria says, and as Sharujan just said, and as Fahad just said, we're going to plug that pi over 6 into the original function. Right? And you tell me what we get this time. Right? What is my y value this time when I plug that pi over 6? So folks, y'all have your calculator. Get those calculator fingers working there. So minus 6 is the original function. Excuse me. Minus 6 times the sine of 2 times pi over 6. What's my, let me drink some water here in the meantime. What's my answer now? Minus 3 root 3 is what I'm hearing from Dario. What do other people think? Before I click that button. And Baroka is saying minus 3 root 3 as well. Okay, usually the first two people are both Baroka and Dario. Wow. Okay. So, yes, minus 3 root 3 makes sense. Okay. So now I know what the x and the y are. These are my two coordinates. Pi over 6 is the x coordinate at the point of tangency, and my y coordinate is minus 3 root 3. But what does that mean now? Where do I go with this? All I remember having was the slope, and now I seem to have the point of tangency plug this into the tangent equation, into the y-axis. Absolutely, absolutely. You've done this before, folks. So the minus 3 root 3 is equal to the minus 6 times pi over 6, because that would be the x-coordinate, and the minus 6 represents the slope, plus the b. So, of course, that would be the b. If you multiply, so this just gives you pi, or sorry, minus pi. Add that to the other side. So what we have as a b is this, and therefore, that's our equation. Minus 6x minus 3 root 3 plus pi. Okay? And that is all we need to say about that question. All right. Thank you, Sharujan, Daria, Fahad, and Baroka, and everybody else who chimed in on that. Fahad.